So today we will discuss together the energy transfer in different forms in case of open and closed system, and we'll talk about several applications related to the energy field. Okay, so to start with, when we did a review on heat transfer processes, we have seen the general energy equation, which will also apply here. So for a certain system, okay, we can write the following: delta E, the change in energy, equals to Q plus W. So this is the first law of thermodynamics. And it states that energy transfer between a system and its surrounding can take place mainly by heat and work. Okay? Now, if we have open systems, we can have fluxes of energy crossing the system, entering and getting out. So then we'll add, if you want to, the common energy terms that we consider. We'll add also, in addition to Q and W, we'll add M dot N. So we have M dot N times energy N plus M dot out times energy out. But again, it's the same idea that any energy or work coming in is positive and any energy or work getting out is negative. Okay? Now, if we want to expand these terms for the energy delta E, it can be in several forms. We know that it can be divided into internal energy, into kinetic energy, into potential, etc. Okay, and depending on the application, for example, mainly let's say in heat transfer processes, we mainly focus on, when we do the study, we focus on the change of the internal energy. If we consider that no change in kinetic and potential, so we mainly focus on change in internal energy, and we relate it to heat and work. Okay. Now, concerning, if you want, let us take applications of this in real life. If I consider first a first example where we can apply this first law of thermodynamics is a closed system. Whenever I'm talking about a closed system, no mass fluxes are coming in or
Hi,
out.
Professor. I joined late.
Hi. Okay.
Hi, Professor
So,
Kishik.
yes, Karim. So, what we have here, for example, let us consider an engine system. Okay. For the case of an engine, what is the main transformation of energy that we have here? What is happening in engines, internal combustion engines? Karim, do you have an idea what happens in internal combustion engines? What is the main form of energy and how we transfer it?
I'm not sure.
Okay, look, whenever we talk about internal combustion engines, we have combustion of air, a mixture of air and fuel within the cylinder. Okay, so we have the combustion energy, which is if you want, it's a chemical energy at the beginning because we have a chemical reaction. Okay, and this chemical energy will be transferred, the combustion will lead to production of energy in form of heat, and this heat, a Q, okay, will lead to high forces acting on the piston, and this will push the piston downward. Okay, and therefore we will transform heat into translation of the piston that will be related to the crank of our crankshaft. Okay, it will lead to rotation of our crankshaft. So mainly we have energy transformation from chemical form to heat form to a mechanical translation and then mechanical rotation. So this is a process that we can study, for example. Okay, any process that I will, you don't have to know before how these processes work, but if I give you a brief description, you can apply on the system the first law of thermodynamics. So in this course, one of the main purposes is to consider different energy systems and to see how energy is transferred from one form to the other. Here, for example, we have a closed system. We don't have mass fluxes, let's say, coming in or out. Of course, if you want, we have admission and exhaust of gases. Sure. But if we just want to do a theoretical modeling of what is happening, we can consider that we have a certain mass of air, and this mass of air is undergoing a cycle. So one of the approach to model in a simple way such systems is the following, is to say, let me see what is happening to air. So I will model air as a closed system that is undergoing several processes. Uh, and if we want to do the analysis of what is happening, we can divide it into mainly four steps. I can tell you first, for example, the piston, the air and within the cylinder will be compressed. So if you want to present this on a PV diagram, you say, I should identify a first state, point one. I have air in my cylinder. Now, my piston will displace between two positions, okay? Bottom, we call it bottom dead center. So the piston is the minimum position that we can reach is here. Okay, this is the lowest level that we can reach. We call that the bottom dead center because the velocity here is 0. Now the piston will move upward, and the volume within the volume of air will decrease. So we are doing compression. So in this phase from 1 to 2, we have compression of air within the cylinder. Okay, so here we have the compression phase. Then I can tell you in such systems, after the compression, okay, once the piston will reach the top dead center, just before it, we give the spark. The spark will lead to ignition of our system. Okay, and we have the combustion. In real life, combustion will take some time, and heat will not be released in an instantaneous way. But because it's so fast, we can say, we can model the combustion process as a process at constant volume. So what will happen from 2 to 3 is that we'll have a big raise in pressure and of course in temperature at constant volume. So I can tell you, you can model combustion of air, of the mixture of air and fuel, as instantaneous increase in pressure at constant volume. And after this, once we have this heat release, of course, here heat will be delivered because of combustion. You have, it's like you are giving your air heat. So air will be heated because of the combustion. So we can consider that we have Qn during this process. Now, the most important phase in our engine system is the expansion. Okay, because during the expansion, when the piston will move downward, it will transfer work to the piston. Okay, so you have the bottom, the piston is moved downward with a high push, and this will lead to translation of the pistons that will be transferred by the rod and crank system to a rotation of the crankshaft. So here I am taking the work, I am transforming, if you want, I'm doing what we call, it's a here it's a power cycle, because I put heat and I take work. I am able to produce a work from my system by just delivering heat to it. So my heat input is through combustion, and my work output is through the expansion of gases, which will push the piston downward. So here we have the expansion phase, and this is what is useful in this cycle. This is the most important phase, because here I have work that will be out of my system. So this is W out. And then let's say this is 0.4. Now from 4 to 1, actually in real life, what is happening is that I have exhaust of gases. This is the real case. But if I want to model it as a theoretical cycle with the same mass going through the cycle, I can model it as rejection of heat, because when you exhaust gases, okay, heat will be released. So you have Q out here. So this is a very simple, if you want, system where I have exchange of heat and work with the surrounding. And we'll learn together that from the analysis of such diagrams, we can come up with calculation of the efficiency of the system and then study different types of engines, etc. Okay. Now, during the compression, we are putting work on the system because, during the compression phase, in order to move up the piston, we want to lose some work and from the surrounding, I mean, and the surrounding should provide work to air, but of course this Wn during compression will be much smaller than W out. This is why in overall W net is positive. This is why I say for internal combustion engines I have a power cycle. So whenever we talk about power cycle, it's a cycle for which the input is heat and the useful output is power. And here we say that if I want to calculate the efficiency of the system, so to express the performance of the system, I can calculate what we call the efficiency. The efficiency, can you tell me what will be the efficiency here?
Doctor, area under the curve.
Yes, very good. So I should consider, but not just the area under the curve. The area under the curve represent W net, the net useful power, okay, that I can produce over what my input. So over my input, which is heat, Qn. So the energy, the heat of combustion is my input, and my useful output is the net work produced by the system. And the network is W out minus W. Okay. Now we will learn together how we can find, for example, the efficiency function of the parameters of the cycle. Okay, so all we have to do then is to use the first law of thermodynamics for a cycle. Whenever you have a cycle, what can you write for the overall system of processes? What is the relation I can put between summation of heat and summation of work for a cycle?
N equals out.
Yes, because if I take each process separately, okay, and I apply the first law of thermodynamics, I can write, for example, the following. So if I just take from 1 to 2, I can say that from 1 to 2, the variation of energy from 1 to 2 is equal to the heat during this process, Q12, plus the work during this process, which is W12. Okay. Now, in general, when we do a theoretical model for engines, we say we can model processes of compression and expansion as adiabatic processes. So whenever we say it's an adiabatic process, you can say that Q is 0. So we can consider that during compression, we only have work that is getting in, and then delta E, the variation of energy from 1 to 2, is equal to Wn. Okay, but if we consider the whole cycle, so because if I start from 1 and then go back to 1, I go back to the same point, so I am with the same state and therefore with the same energy. So whenever we consider a whole cycle, delta E for a cycle is 0, because I am back to the same point, which is characterized by the same energy. And this is why when I take a whole cycle, I should put delta E equal to 0, equals to sum of Q over the whole cycle plus sum of W. Okay, so here, if I consider the whole cycle, I can say that Qn, which is the heat input during the combustion, minus Q out, which is equal to the heat rejection during the cooling phase, which is related to exhaust of gases in the real case. Okay, plus Wn, which is the work we put in compression, minus W out, which is the heat, which is the work that is given by the system to the crankshaft, equals to 0. Okay, and if we we should pay attention why we didn't consider in 1, 2, and 3, 4, we didn't consider any heat, because they told us that these compression and expansion are adiabatic processes. Now, who can tell me why between 2 and 3 and 1 and 4 we didn't consider the work? Do we have work from 2 to 3 and from 4 to
Because
1?
the volume didn't
Constant
change.
volume.
Yes, very good. You know that the work is calculated as integral PDV. Okay, and because the volume didn't change here, then during these two phases, no work. Okay, so we can deduce that Qn minus Q out, so Qn minus Q out is equal to W net.
Yes.
Okay, so now if you want to express W net, if you want to express the overall efficiency here for the thermal efficiency of the system, the thermal efficiency, you know why I'm just saying thermal efficiency? What is the difference between the thermal efficiency and the overall efficiency?
I don't know.
Okay. We have that in general, you know, if we take this example, the thermal efficiency is just related to the cycle that you have, which is for which the mixture of air and fuel is undergoing. But you know that to have transmission of your work from the piston to the rod to the crankshaft, you have losses. You have mechanical losses, okay, you have heat losses. So if we want to calculate the overall efficiency, we should consider all these losses. Okay, so we should consider another efficiency factor that in general is determined experimentally. But if we just study the cycle, we can talk about the thermal efficiency, which is W net over Qn. Okay, and now if we just replace W net by Qn minus Q out, then we get a simplified form for the thermal efficiency, which is 1 minus Qn over Q out. Okay, and in general, the efficiency of a thermal engine will be determined from ratios that are characteristic of this engine, and we'll discuss this now. In general, we talk about the ratio of compression. What do we mean by the ratio of compression? If you look at the following figure, okay, we said that the piston will be displacing between two positions, top dead center and bottom dead center. So we have like a maximum volume at point 1. So let us call it V1, which is the maximum volume. And you have a minimum volume at V2. So in general, one very important factor that characterize a certain engine, and it will be affected if it is a diesel engine or a gasoline engine, is epsilon. And epsilon is just the ratio V1 over V2. Larger the ratio, will demonstrate now together that larger this ratio, larger will be the efficiency of our system. Okay, we will try together to relate the efficiency to epsilon. Please, guys, can you mute your microphones if you don't have questions, please? So the question is to express the efficiency here, function of the compression ratio of the engine, okay, and function of the coefficient K. What is the coefficient K? Whenever we have adiabatic phases, we can say that for adiabatic phases, the equation is PV to the power K, which is the polytropic expansion coefficient. PV to the power K equal to constant. Okay. So in general, for any fluid, for example, each fluid is characterized by a certain value of K. And sometimes also K varies with temperature, but here we'll assume constant value of K. Okay. So if we consider K to be constant, for the two adiabatic processes, which represent compression and expansion, we can write that the relation between pressure and volume is PVK equal constant. But if I tell you now relate the efficiency to epsilon and K, how can you start? How can we incorporate epsilon and K to our analysis here? Any idea? Okay, look, first, always let us see what is Q out and Q in. We should try to relate this heat exchange with the states. And here for Q out, you are going from point 4 to point 1. Okay, and from the review of heat transfer, we have seen that energy exchange or heat exchange can be done, but can be sensible, can be latent. Okay, in this example, we have sensible heat exchange, and we know that in case we have a gas during a constant volume process, we can replace Q by mCv delta T. Okay, so we can say that Q out is the mass of air times the specific heat at constant volume times delta T for process from 4 to 1. Okay, so times delta T between points 4 and 1. Okay, over Qn, because the heat input is from 2 to 3. Okay, so over mCv times delta T from 2 to 3. Just here, please pay attention, because here we are considering the absolute values of Q, because we already said it's out. Okay, yani Q out is positive because already the arrow is outside of the system. So we will take the absolute value of delta T from 4 to 1 and the absolute value of delta T here from 2 to 3. Okay. Now, we can see that M and CV will cancel out, and we'll end up with the following. We'll be able to simplify our efficiency to the following expression. So again, this is our cycle. This is 1, 2, 3, and 4. Of course, T3 is larger than T2 because here we have the combustion, so increase in pressure and temperature at constant volume. And T4 is larger than T1 because here we have the cooling of our air. So we can consider then that the efficiency is 1 minus, we said we consider delta T between 4 and 1. So we'll take the absolute value, so T4 minus T1 over T3 minus T2. Okay. Now, we are still far from what we want to reach. We need to incorporate epsilon and k. Okay, this is why we should go back to the processes that we have. We didn't use yet that these two processes are adiabatic. So because these two processes are adiabatic, this means that PVK equal constant. Okay, so because PVK equal constant, we can write the following. First, between 1 and 2, we can relate pressures and volume. So we can write that P1 V1 to the power K equals to P2 V2 to the power K. Also, we can apply between points 3 and 4, we can also apply this relation. So we can say that P4 V4 to the power K equals to P3 V3 to the power K. Okay, but as you can see, we have that V2 is equal to V3. And also from 4 to 1, V4 is equal to V1. So if we divide terms here, we can simplify V1K, V4K that are equal, and V2K, V3K. We deduce that the ratio of pressures P4 over P1 is equal to the ratio P3 over P2. But since we want to include temperatures, okay, we can say that from 4 to 1, we have a process at constant volume. Okay, and from 2 to 3, also we have a process at constant volume. And we will deal with air as a ideal gas. Okay, so assuming ideal gas behavior, so for ideal gas behavior, we can consider that PV equals mRT. So if we take a process at constant volume, we know that the mass is fixed, the volume is fixed for this process, R is a constant for the gas, so it will not change. So for V constant, for V equal to constant, we can say that the ratio of pressure is equal to the ratio of temperatures. So from here we can deduce that P over T is constant for a process of constant volume. So we can write then between 2 and 3, we can say that P3 over T3 is equal to P2 over T2. And from here, we can deduce that the ratio of pressures, P3 over P2, can be written as the ratio of temperatures. So this is equal to T3 over T2 and equal to T4 over T1. Okay? But until now, still, it's not very clear how to relate to epsilon and K, but at least I was able to relate the pressure variation to the temperature variation. And I can see that I need ratios. if I can figure out ratios in my expression here, I can reach what I want. This is why working with ratios will simplify things a lot for you. All you have to do, you can take any temperature and factor from both sides. Yani here, for example, I can say, let me take, for example, here a T1 as factor. Okay, so I have 1 minus, if I take T1 into factor, I get inside T4 over T1 minus 1. Okay, and for the denominator, let me take T2 as factor. So I will have T2 factor, T3 over T2 minus 1. Okay, so now I can say the following. First, when I did my analysis, I come up with equal ratios. T3 over T2 and T4 over T1 are equal. So I can cancel out these two terms. And now my efficiency is so simplified. I just have to determine my final ratio, which is T1 over T2. And to do this, I go back to my figure. Points 1 and 2 are relative to the compression phase. Okay? And during compression, we have that PV, it's an adiabatic process, PVK equal constant. Okay? But also during, for adiabatic processes, I can deduce a relation between V and T. Because we know that for ideal gas, PV, guys, please, guys, can you mute your microphones, please? So PV equal MRT. This means that I can replace pressure in my expression here by MRT over V. Okay, so if you replace P by MRT over V, you get the following. You get MR times T times V to the power K minus 1 equal to a constant. And since M and R are constant, so I can also take them from the other side. And I deduce that for a constant, for a adiabatic process, I can also say that TV to the power K minus 1 is constant. And now I can relate the ratio T1 to T2 to the ratio of volume, because from 1 to 2, since it's an adiabatic process, I can write that TVK minus 1 is constant. So T1 times V1 to the power K minus 1 is equal to T2 times V2 to the power K minus 1. Okay. And now I want the ratio T1 over T2. So this is what I want. T1 over T2 is equal to V2 over V1 to the power K minus 1. And if you remember, we said that an engine is characterized by this ratio epsilon represent V1 over V2. So we can replace V2 over V1 by 1 over epsilon. So the ratio of temperature is 1 over epsilon to the power K minus 1. So now we were able to find the efficiency just function of epsilon and K. And the thermal efficiency of this gasoline engine is 1 minus 1 over. So as expected, if you increase the compression ratio, so for larger value of epsilon, the efficiency will increase. Okay, so this was an example of a closed system that is producing power. So it's a power cycle. Now we'll take together other examples of, let's say, if you want, open systems, okay, that can also produce power. Okay, so now this was the first example of a closed system. Before taking another example of closed system, I will talk a little bit about open systems. Open systems, as we mentioned before, are systems where we have fluxes of masses coming in and getting out. So you can take any mechanical equipment, let's say a pump, a turbine, etc. Whenever you consider it as your system, you have fluxes of energy coming in and other getting out. So let us take the turbine. We know that in general, the turbine will do what here? The turbine is here to produce work, okay? And in general, for majority of cases, we can produce electrical work because the turbine will rotate a shaft and the shaft will be related to a generator. So we can convert the outlet work, which is a mechanical work, into electrical work. So here also we have conversion from one form to the other. Now, how will this happen? We have a flux of fluid that is coming inside the turbine at a certain mass flow rate, let's say m dot n, and it's characterized in general by high internal energy. Okay, and you know that whenever we work with open system, we can consider that the overall energy coming in can be lumped into m dot n hn. We will discuss this together now. And what is getting out is m dot out h out. But in real case, the enthalpy is nothing than two terms that we lump together, because the enthalpy is combination of heat and work, as we'll see together. Okay, so here we have mass fluxes, and this is why it's an open system. So when we consider the equation is still, if you want, the same. It's the conservation of energy, but we should take into account fluxes getting in and fluxes getting out. Okay, now we know that the general form of energy is the following. So we write delta E. Delta E stored, okay, is equal to sum of Q plus sum of W. Okay, here what we add here is the energy of fluxes coming in minus the energy of fluxes getting out. So we have plus sum of En minus sum of E out. And in general, okay, we know that this is the energy equation. In general, the units are in joule. But whenever we talk about mass flow rates, in the majority of cases, we use the rate equation. So sum of Q dot